seven, six, five, four, three, two, one. Liftoff.
Hello guys, this is Paul McWhorter from TopTechBoy.com, and we're here today with our live shop talk number 9, where we are going to be talking about nanotechnology, MEMS, and micromachining. This is really part 2 of our most unfortunate part 1, where we had a power outage in the middle of it, and I mean the power went down hard. And so I'm sitting there showing you all of these amazing little microscopic machines, and all of a sudden the power went out and I could not even log back on. I didn't have anything to even get back to YouTube so that I could leave a message that the power was out. And so it was just kind of like this blank live stream. But appreciate that you guys are patient, and I appreciate that you guys came back. Looks like we've got some people coming in. Conan is here, and it looks like we've got Maniac at the controls. Ray, hey Ray. A foreign script that I cannot read. It looks quite interesting, but I'm not able to read it. Umar is here. Sethu is here. All right, guys, it's great to have you. How many of you guys were here for Wednesday's show, or at least watched it, part 1 of this? Because I can't go over all of that material again, but I'll give you a quick recap. Yes, I will need you to pour yourself a nice big mug of iced coffee. Do you guys have your coffee ready? Okay, let's see. Ray, good to get a backup. Yeah, it'd be nice to have a backup power supply. If you guys would go over and help me a little bit on Patreon, I could get some of this stuff. I want to thank you guys. A number of people have come through and tried to help me on Patreon. There's a link down in the description, and that's a great encouragement to me, because man, I don't want to do this if it's not useful, and if it's not useful, then I'm just wasting my time. But if it is useful, go over to Patreon and hook a brother up. Okay, just help me out a little bit over there. All right, that's enough of that. That's enough of that nonsense. Hey Charles, I watched part 1. Yes, I remember you were here, and I do appreciate your encouragement very much. PS4, you watched a little. What is this watch a little? I am showing you great technology. You need to go back and watch that. Okay, Charles has got his coffee. Okay, Sethu, yes. Ray has tea. Ray, please tell me you don't have sugar in your tea. Okay, hot tea, cold tea, but please no sugar in there. Okay. Hope you're doing that. Okay, you guys watch that. All right, and I appreciate you guys, but let's just jump right in. And how did we end up talking about nanotechnology? Oh yeah, man, are you guys tuning in to our inertial measurement unit lessons? I got a lot of hate on that. I got like 4 thumbs down. I never get 4 thumbs down on a video. How come I got so much hate on lesson number 1 of my IMU tutorial? The only thing I could figure is that people were maybe expecting it to be the next lesson in the Arduino tutorial, and they got mad. Or maybe they were expecting me to do the whole thing in one lesson where I was just introducing what I was going to do. Or maybe it's like everyone was complaining, why did you go back to your old microphone instead of the nice high quality Blue Yeti microphone? Okay, people were complaining about that. Is my audio okay? My meter looks a little bit low. Okay, let me know how my audio is and if I need to crank up a little more gain there. I think I should turn it up a little bit. So I guess the other thing is people were saying, how come you went back to your old microphone? Well, you got to remember, I record these lessons, sometimes a whole bunch in a day, and then I release them one at a time. Now, here we're actually live, right? But I release them one at a time. So I don't know why I got so much hate on that video. I thought it was a pretty good one. Okay, yes, I watched the part 1. Okay, does Red Bull count? No, Red Bull will kill you. You need the caffeine, not all that sugar. Okay, Raspberry Pi. Okay, I got the BNO 055 still stuck in customs. Oh, Charles, I'm sorry. Okay, yeah, I know some of these high-tech parts can be an issue. Okay, audio good? Okay, good. All right, so I get a little feedback. You guys have to understand, between me and you, there's about a 30-second lag. So when I ask a question, it takes 30 seconds for you guys to hear it and respond. And so that's why I kind of blather for a while. I wish this was more real time. Yash, I don't remember you, Yash. Where do I know you from? Yash, how would I know you? Okay. No, the sensor is very expensive for me, but I still like the information. Guys, but the thing is, it does some on-chip processing that is really, really hard to do on your own. And so I have had like almost every 9-axis sensor that is out there. And man, if you really, really want to do that full 360 show that I'm showing you, you really need that sensor. I decided to not get Charles? To not get the Jetson Nano for now. Expensive and not enough to learn and play with for now. By the time I get the Nano, there will be a new one already. Okay, I understand. Man, I really am getting excited about the Nano, and I'm doing some really cool stuff with it. But what I want to do when I go on the Nano, this is the Jetson Nano, I want to teach you artificial intelligence from ground zero. So I'm going to assume that you're smart, which I know you are. I'm going to assume that you're a hard worker, which I know you are, but I'm not going to assume that you know anything about these complicated environments and packages. So I'm going to start at the beginning and take you through step by step. Also, we're not going to just download someone else's demo package and figure out how to run it and then, try to impress our girlfriend with what the little thing that we installed did. No, we're going to be developing our own code. And I've gotten to the point that just starting from scratch that I can start doing some recognition and tracking. And so I've got some cool projects that are in mind there. But I have not seen a lot of love as far as this tutorial goes. So I am not committing yet to doing a Jetson Nano tutorial till I see that there would at least be someone who would be interested in it. Okay, don't worry, people will always complain. Yep. Yes, sir, they will always complain. Hi, Bob. Always good to see you joining us. Please make a playlist on Raspberry Pi for beginners. Man, it's already there. Look at my channel. Look at my playlist. Look at Raspberry Pi. I do need to freshen those up at some point. The B&O 055 does everything. Now we're going to do a lot of stuff from scratch, but it will do everything, and we will eventually get to there. Yashti, I'm from India. Love your videos. Please make one on gyroscope. I was the guy who asked you how to build. Okay, yeah. All right, Yash, I remember you now. Okay, so this is why I'm rambling too much. We need to get over and we need to start talking about nanotechnology. So let's show the show here for a second, if we can. What is this nonsense? Where are we? Okay, that should work. All right, so this is the show. Come on. Okay, it's a little slow today. And that is not what I wanted to see. Guys, let me adjust this. I am kind of a stickler for my windows being just the way I want them. Okay. There we go. Okay, so this is what we're doing in those IMU lessons. I am going to show you how to build a simulation where whatever you do with an object in the real world, the object in the virtual world will track it. And there's all types of cool stuff. You could put this on your head, and then you could track your head. You could make a mouse that pointed based on where your head was. You could remotely control a camera that was on two things. You could point a laser. There's all types of things you can do when you get this type of stuff. Now, there's other guys that will show this, okay? But on those other videos, I want you to watch. They'll go like this, they'll go like this, they'll go like this, they'll go like this, they'll go like this. Small angles. The hard thing where you really have to do the math is who can go all the way horizontal and then spin. Who can go upside down? Almost no one. Okay, so you're going to get the whole full-blown solution on this. And this is why I got the B&O 055, that it has some helpers on there that will allow you to take things to this level. How does this thing know where it is? Nanotechnology. Nanotechnology is how that thing knows where it is. And I know a lot of you guys watched. Let me go back and just kind of see the chats coming in here. Delicious. Inferno, I hope you're talking about coffee. Just so much to learn. Charles, yeah, I know. If you do make the course, I will get the nano. And hey, yeah, Charles, that's what I want. Let's try to get through the B&O. So what I'd like to do is, I'd like to, and you guys give me feedback, because the guys that tune into the live chat, you're my boys, right? You're kind of the inner circle here. So I want to hear from you guys that are the real enthusiastic members of the, this little community that's developing. What I'd like to do is I'd like to have a beginner's tutorial track, and then I'd like to have an advanced project track going. So right now we have those our introduction to Arduino tutorials, and then we have the B&O 055, which is more advanced. When that B&O 055 gets done, then I would really like to do something on the Nano, because I am getting very excited about the Nano. And you're sitting here seeing my control room. I did not know that. I should give you something else to look at other than the control room. You want to see my yard in Africa? I'll show you my yard in Africa. This isn't live, but this was recent. Out chopping the grass. Happy little place there. All right. But let's come back here and let me see if I can look at your questions. What kind of, let's see. Hey, Mike Rubino has the Jetson. I have Jets on Nano. Do you have a Jetson Nano, though? Thanks for your videos. Really interesting. I'm working in nanotechnology, but in pharmaceutical field. Hey, I had a company on biomedical MEMS where we did implantable biomedical devices with MEMS. Okay. Can you suggest some science books like Brief History of Time? I don't read books because, well, I read the Bible, but the problem is by the time books are published, they're out of date. So I do a lot more stuff on the on the internet. I'm interested. Okay, Mike is interested. My full name is Yes Dangit. D for dang it. Okay. I was talking about AI lessons. They sound delicious. Okay, I was hoping you were talking about coffee. So no gimbal lock on your B&O? No gimbal lock. Okay, no gimbal lock. Why? Because I use quaternions. All right. Those avocado trees. Yes, sir. Those are avocado trees. Let's see. I actually planted about 200 trees. There's that tall one in the back is avocado, mango. I got a lot of moringa trees, macadamia nut trees, cashew nut trees, just any tropical coconut trees, dates, palms, any imaginable tropical tree I have planted there. But I digress. I was answering a question. I thought you were in the U.S. Northwest. Do I look like a Northwest person? No, sir. West Texas. Born, bred, okay. But then I spent a lot of time in Africa. Hello, Chun. Okay, let's get back to, you guys are distracting me with all these interesting questions. Let's get back to nanotechnology, okay? So what is nanotechnology? Nanotechnology is taking the facilities and tools and manufacturing infrastructure that were developed to make integrated circuits, like Intel chips and computer chips. But instead of building microscopic electrical devices, we thought, well, hey, if I can make, how did I get so small? That was too small. Okay. Hey, if I could make a microscopic electrical device like a transistor, why not use those same pieces of equipment and manufacturing facilities, but build microscopic mechanical devices? And so what we did was we started developing these ways to build mechanical elements in a microelectronics clean room. And so that was kind of the inception of the idea. And to give you an idea for things that we actually built here, I showed this picture earlier last time, but I'll show it again. This is one of the microscopic gears that we built next to some human red blood cells. So you see, we're building machines that have mechanical elements the size of a red blood cell. And I think you can get kind of a better look if I show you some scanning electron micrographs. You know, a scanning electron micrograph. Hey, Francis, man, how's it going, buddy? Haven't heard from you in a while. How are you doing? Everything good? Francis. All right. Always good to hear from Francis. Okay. Everybody is saying they're sorry. I'm not sure why you're saying that you're. Oh, sorry that you thought that I lived in the Northeast. Okay, I'm not sure why everybody's saying sorry. Okay, so anyway, this is one of the gears that we built using nanotechnology. One of the very early things that we did. Again, I have a lot of patents in this area, so I did a lot of the very early work. This is a scanning electron micrograph. What in the world happened there? That was crazy, wasn't it? That was kind of frightening. Wow, it does not like that picture. Let's see if it does this. Well, I've got some craziness going on here. Let me see if there's any way I can fix that. Or if we're just running into... Are you guys getting a crazy image there? Let's see what's going on. Technical difficulties, yes. Okay, it looks like it doesn't want to show my images. All right, I'm not sure why it doesn't like these pictures. Okay, like that one. Let's see if I can go to something blank and then come back. Man, the world of high technology. That, my friend, is not nanotechnology. This darn thing. Okay, let's go on and persevere. Let's see if we can go back to, let me see if I can go back to, I'm not exactly sure what you guys were seeing there. Looks like the file is corrupted. Yeah, but you see, the thumbnails are right, but it is, India has reached to Mars, but Pakistan is still trying, okay, guys, let's be nice, right? We want Pakistan and India to get along. Okay, can we all just get along? Okay, we want everyone to get along. I like everybody. I like the Palestinians. I like the Jews. I like the Indians. I like the Pakistanis. I like everyone. Let's try to get along, guys. Okay. Now, all right. At least I can get back to these backgrounds. Let's see. What I want to do is I can just kind of remind you of some of the early stuff that we built. And so let's see if I can get a video up here. And we will see if we can get this going. I showed this last time, but I want to show it again just so that you can kind of see the thing. Because also I just thought this was really cool. So this is really from a microscope. And this was kind of like just to emphasize to people in the early days, we wanted to show them just what we could build, how complicated of a thing that we could build. So I decided I'm going to build the world's smallest merry-go-round. And to show that it was real, we needed something really, really small to ride it. So we got dust mites. Where do you get dust mites? Well, they're everywhere, right? You have dust mites on you. They're like little, they like keep the world clean. They go around and they clean things up. So dust mites are everywhere. So we got a dust mite, and we decided to see if we could make him take a ride on the world's smallest merry-go-rounds. Yeah, I think actually I got like a bandwidth problem. I should have rebooted my computer before I started this thing, because this is really slow today. And I actually have a nice computer, but this broadcast software really uses a lot of bandwidth. Okay, so we tried to make the world's smallest merry-go-round. You can see the dust mite ran by. Next time he ran over it, did you notice when he ran over it, he was carrying a little piece of a micromachine and he dropped it on the merry-go-round there? But the next guy's going to come up, and he's going to come and we're going to give him a ride around. Now, this is the first time, the world's first time, that a dust mite ever rode a merry-go-round like this, and so this was an important first. But the first time we wanted to go real easy. We wanted to like see, kind of see if we could give him a ride around. So the first time we went really, really easy on him. We went forwards and backwards, and then we stopped, and when we stopped, he ran off, okay? But after that first success, we decided, hey, I wonder if we could really spin him up, and if we could make him dizzy. So on this one, we're going to spin it, and now we're going to take it to a couple of thousand RPM. We're really going to spin him up to a couple of thousand RPM, and then we stop and go back and forth and shake him around. And yes, indeed, he did get dizzy. He was okay later on, and he ran off. No dust mites were hurt in the filming of this. And then this is an aphid. Okay, the aphid is a big, ugly monster. These things look horrible under magnification. But you can see that as he was walking over this machine, we were running it. So we had some fun with those. So that was back in the early days. And back in the early days, what we were doing was we were just trying to create on a microscopic scale the things that you would build in the real world. So we started making motors, and we started making gears, and we started making transmissions, and we started making just a whole bunch of different stuff, just trying to create on a microscopic scale the machines that you would see in the real world. So some of the things that I think where we left off last time, let me just give you a quick recap of how we would make these things. Okay, the way we make these things is we use the same manufacturing facility that you use to make integrated circuits. And man, one day I need to really just give a series on how integrated circuits are made and kind of give you the full story on computer chips and how they're made. But for right now, the way it's done is you start with 6-inch silicon wafers, and then you make things. There's two characteristics of integrated circuits. The features that you're building, the little transistors, which are little electronic switches, are very, very small, and then there's billions of them. Okay, so the two characteristics of integrated circuit manufacturing is you make things really, really small, and then you make a bazillion of them at a time. They're batch fabricated, so you don't individually make anything. The wafer goes through the manufacturing steps, and it comes out with all the transistors made, all of them hooked together, all of them. Oh, I'm always going to knock something over, right? It's always going to get something knocked over. All right, but at least it was not the coffee. That is the bad one, is if I knock over my coffee. So the two characteristics of integrated circuit manufacturing is, number one, you make things really, really small, and number two, you make a whole bunch of things at the same time. Okay, so those are the two characteristics. How do we get small? How are we able to make things so small? Well, I draw something in the real world, so I'm going to draw a transistor. And now my camera is going to be probably all messed up. Well, at least it's still working. That's good. Let me see if I can kind of get it lined up there. Okay. And I need to get it to focus. Oh, man. You know how I hate it when this thing doesn't focus. You got to give it something to see. Let's see, like this. Okay. Then you got to gradually bring it back and then give it something to hold on to there. So I might just leave this here so it has something to focus on. It doesn't like seeing something blank. So the way that you would make a transistor is you could draw the gate of the transistor like this, and then you could draw the source of the transistor like this, and then you could draw the drain of the transistor like this, okay? And you see I'm drawing it in the real world, okay? But now what I could do is I could take this and I could make a negative, and then I could project light through it, and then with optics I could take it from being this big down to very small fractions of a micron, like 1/10 of a micron or less than 1/10 of a micron. But it's done optically. You draw it on the computer screen, you make a negative, and then you optically reduce it down to very, very small dimensions. So it's done with a lens, just like you look through a telescope and it makes things big. Well, if you look through the other end of the telescope, it would make things small. So it's like you're projecting through a telescope backwards would be a way to do it. So that is how you get small. It's done optically. Okay, now how do you get many? Well, I could make this transistor, and you could think of it as a black box, and then you could copy and paste it, and you could put 5 transistors together, and you could get one memory cell, like one bit of memory. And so now I'm not designing with transistors, now I'm designing with bits. You could put 64, cut and paste that bit 64 times. Now you have a byte. Now I've got a block that's a byte, and then I could put those things together and you got a memory. So you see, you get many by cutting and pasting, but they're all the same thing. It all comes down to a transistor, but you're just building these blocks up. So you get small by doing things optically, and then you get many by cutting and pasting. Well, it's the same thing with making the micro machines, that if I built a little motor, okay, if I built a little motor, then I could cut and paste this, and then I could have a bazillion of them across the surface of the wafer. And that's why you can get something like the B&O 055, and it's an extremely complex mechanical micro machine, okay, but it's low cost because they're built a bazillion at a time across a wafer. So, guys, I'll get back to your questions in a minute. But one of the things that we ended up with last time is, how do you build the motors and how do the motors work? Okay, we build the motors the same way that we build an integrated circuit or a transistor. You have a silicon wafer. You start with a blank silicon wafer. And then what you do is you deposit thin films on it. Then you photo pattern those thin films, and then you etch those features that you photo pattern. So you deposit, photo pattern, etch. Then you do it again, deposit, photo pattern, etch. Then you do it again, you deposit, you photo pattern, you etch. Okay, so you do that over and over, and then you just start building these machines up layer by layer by layer. And of course, again, I have lost my focus. Man, if anybody knows how to keep a webcam in focus, leave a note down below. Okay, leave a note down below if anybody knows how to keep a webcam in focus. Okay, so like to make a, let's say I'm going to make an accelerometer. I start with a silicon wafer. Okay. I start with a silicon wafer, then in cross section, I put silicon dioxide down. I grow silicon dioxide. I cut open the silicon dioxide. Okay, silicon dioxide is glass. So I have silicon dioxide, and I have a hole in it down to the substrate. Then I deposit polycrystalline silicon. Okay, and the polycrystalline silicon will deposit down into this. So it'll be like this. Okay, so that's polycrystalline silicon. All right. And then what do? I photo pattern the polycrystalline layer that I put, so I end up with a well-defined diving board. Okay, so I have a well-defined diving board. All right. But now what is the problem with this? It is sitting on top of the silicon dioxide or glass, so it can't move. So what do? I dip the wafer in hydrofluoric acid. That does not etch polycrystalline silicon, but it etches silicon dioxide or glass. And so then what I end up with is this diving board that is anchored to the substrate here, but here it's free to move. So as I move this thing like this diving board is going to respond to that by moving up and down, and this gap is going to change. All right. Well, I can measure the capacitance between here and here, and capacitance is equal to epsilon A over D. Epsilon is a constant, A is the area of the capacitor, and D is the gap. D is the gap here. And so by measuring capacitance, I can measure D, okay? And then D, the change in D is proportional to let's put it up here. The change in the D is proportional to the acceleration. So if I measure change in D, I can calculate A. Boom! I just made a nanotechnology accelerometer. And when we look at the BNO 055, it has 3 accelerometers on it. It has 3 gyros and it has 3 magnetometers. Now, it's a, you can imagine it's a lot more sophisticated than this, but this illustrates the concept behind how the accelerometer works. All right. Then somebody was asking, how do you make a motor? All right. So how does the motor work? Like the little motors that I was showing. Remember the little motors that I was showing in the video? How do you make the motors? Okay. Let me see if I can show you how to make the motors. Now this is the trick with motors. In the real world, you use magnets because magnets are cheap, they're easy to work with, they're powerful, and it's easy to get a spool and a big piece of wire and wrap things around. So motors work magnetically in the real world. Here's the problem in the microscopic world. In the microscopic world, you are living in flat land. Okay, you're living in flat land. Everything is kind of two-dimensional. Now, I can draw a gear and I can make a gear, but I could not wind things around by using the process of depositing, photopatterning, and etching. All I can get is flat layers on top of each other. So something like a magnetic motor isn't going to work because you can't wrap it. The other thing that's not going to work very well is, right, you can't go build a $10 billion clean room to play around with nanotechnology. You've got to go into a facility that already exists, and they're not going to let you bring in any strange material and mess up their clean room or their fabrication facility. So you've got to kind of use the things that are already there. So magnetics was a non-starter. We couldn't build magnetic motors. But what we did was we built electrostatic motors. Do you guys remember back in the day you would get a balloon and you would rub the balloon on your hair and it would put charges and then the balloon would stick to the wall? Or you know that positive charges repel and a positive and a negative charge will attract? Okay, that's electrostatics. So since we couldn't use magnetics, we used electrostatics because that works real well in flat land. And so this is what we are going to do. We are going to build sort of a comb structure, and I'll just show you 3 fingers, okay? And so, but imagine that this comb had millions of fingers, okay? But we're only going to draw 3, okay? This is off to a very poor start, okay. Okay, do you see that this is a comb? And this is anchored to the substrate. So if I looked at the side, if I looked at the cross section of this, this comb is sitting on the silicon wafer like this. Okay, it's sitting on the silicon wafer. It's not floating. And then over here, I'm going to build another comb. And you know what? This comb is also sitting on the substrate. So this guy is not floating. Okay, so this is sitting on the substrate and this is sitting on the substrate. But if you looked from the side, it does have thickness. You know, it's got like 2 or 4 or 6 microns thick, but it's just sitting there. Now what I want to do is I want to build a comb, but this comb is not going to be sitting on the substrate. It's going to be like that diving board. It's going to be floating above the substrate, but I want it free to move, so I'm going to suspend it from these tiny springs. Okay, so what I'm going to do here is I'm going to build a tiny spring like this, and then a tiny spring like this, and then I'm going to build a tiny spring like this and a tiny spring like this. Okay, and you notice that they are flat. Now for it to really be springing and move, it's got to be a lot longer than what I've drawn it here, but that is a spring, okay? So this is, those pads are anchored to the substrate. So like here, 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 and here, those are anchored to the substrate, you know, like this. You know, these are anchored to the substrate, and these are anchored to the substrate. So everything I've drawn so far is anchored to the substrate. I think I'm going to draw in blue the things that are not anchored, the things that are floating. So the springs are floating. Okay, these springs are floating. Spring, spring. Okay, and then spring, spring. Our springs are floating. All right. Now I'm going to build this comb structure like this. And this comb structure is floating, and it is suspended by these springs, okay? Okay, so this whole thing is floating above the substrate, and it's free to move. And because these springs are longer than I've drawn them, this thing is free to move around. Okay, and also I can make electrical connection to this because this is connected to the substrate. So I'm going to just say, let's say that I ground that. I ground all of these pads. Okay, then also on this that's connected to the substrate, I can connect this to a voltage. So I'm going to come here and I'm going to connect this comb to 5 volts. If I put 5 volts here, that's what kind of charge? That's positive charge. If I put this as a ground, that's going to pull electrons in because this plus 5 volts is going to attract electrons. Okay, so I've got pluses and I've got minuses. What's going to happen? Electrostatic attraction, and this thing is going to pull this way. So I just created a little motion. All right. Now, you think, well, put a negative voltage and it'll repulse. No, if you put a negative voltage, you're going to pull positive voltage in it. So if I put a positive voltage here, it's going to attract. If I put a negative voltage here, it's going to attract. So if I pull it this way, how do I push it? How do I get it to go back the other way? Well, that's why we have 2 combs. I would ground this one, and then over here I would put plus 5 volts, and then it's going to pull it this way. And then put 5 volts here, it's going to pull it this way. So putting 5 and 0 and 5 and 0 on those 2 combs, that's going to move back and forth. Now, because I can't fit too much on my board, just imagine that these were really long and the springs were really long. Then you can get good motion. So this is called a comb drive, and what you do is you create this little platform that has all these fingers on it, and you can move it back and forth. Okay, well then how did we make the gears that spun? Now I'm going to make that little comb drive just a black box. Okay, so it's a black box, and it has something that comes out that will move back and forth because it's connected to the comb drive in this black box. And then over here, I've got a comb drive going this way. Okay, well, what do? I just make a gear with a pin here, and I connect here and here, and it's like the old train. With just the linear motion this way and the linear motion this way, you can make that wheel go around. Now, for a train, there was just one linear actuator because the train had momentum. So when you got to that dead spot, the momentum would take it past it. But here, there's no momentum because these gears are so small. So we had to have orthogonal actuators, one going like this and one going like this, and then we could build this thing. Okay, so that's how we built the motors. Everything's built in flatland. We build linear actuators, and then we can convert the linear motion to rotational motion. Hey, let's get back and look at some of your questions. You guys, now would be a good time to talk about questions, and maybe I'll come in and kind of talk to you a little bit more about how the B&O 055, how accelerometers and gyros actually work. Okay. Good news is it seems like we're still online. We haven't crashed. Always when you have something start malfunctioning, you start getting scared that the whole thing is just going to kind of come to pieces. All right. Let's see. I'm trying to go back and see if I can. Okay, somebody, Chun is allergic to dust mites, I think. Yeah, it's okay. At least we can resolve this issue between us. Okay, yeah, we're all going to get along, right? This is science. Yes, sir, this is science. Those machines are almost invisible. Those machines are invisible to the naked eye. You cannot see red blood cells with your naked eye. Okay, so yes, these things are so small they're invisible. Okay. Yes, this is pretty neat. Okay. What is this attraction called? I'm not sure which attraction. Yeah, dust rides. Okay. I'm not an Athenian or a Greek, but a citizen of the world. Oh, okay. Socrates. That's very interesting. Yeah. I used to, I don't know, I used to like collect antique maps, and I had a website with maps, and I'd put a map up that, I don't know what it was, but there was like a map of Constantinople. And what is there's like something between Turkey and Greece and like Constantinople versus like is it Istanbul or something? Was there like one city that at one point was one name and another? And it's just like, oh my goodness. I showed an old map that used the old name, and it really, really made people very, very upset. Okay, always has focus. Yeah, I do always have focus problems. Maybe that should be next project. Intelligent focusing. Yes. Would somebody figure out how to get a webcam that will actually focus? If a bit holds a 0 or 1, then how does it hold it? Is it okay? How does it hold it? All right. Let me see if I could try to explain how you hold a 0 or a 1. So you know a transistor is either on or off. And I'll try to kind of draw this, okay? But like if I make this as a transistor and then this is a transistor, I'll do it for real one day where I can really show you, okay? But you would have like, oh man, you can't see what I'm drawing. Are you guys screaming at me? Okay. How do you hold 1 bit? Okay, well, it's like you take 4 transistors, and then it's kind of like you sort of tie them something like this, and I would have to think about it. But you're sort of crossing your connections, and then if you come in and pulse this high, then this turns on, which makes this high, and then if this is high, then this one's connected to ground, so this would be like low and this would be high. But if you put the pulse over here, then it makes this one high and this one low. And guys, I'll make another video just on this so that I can step you through it where it works, but it's sort of like you have 4 transistors cross-coupled with each other, and then when you put a pulse on them, you flip them. Okay, and then you just define which state you're going to call a 1 and which state you're going to call a 0. But this will work until you take power off. Once you take the power off and come back, these things can't remember where they are because they just go back to wherever they were. They can't remember. Now, the way you would remember where you were with like non-volatile memory, here's the substrate, okay, and then here's the gate, and then here is an insulator. Okay, so this is the gate of the transistor. If I put a very high voltage, like plus 20 volts, I can inject charge into this insulator, and it sticks because charge isn't supposed to be in an insulator. So I can come back later and I can see that charge there. Or I can flip it the other way and I can put positive charges in there and I can take the voltage off. So you inject charge into an insulator, and that's how you have memory that doesn't forget things. Okay, that was a good question. We really need to do a whole separate thing on. What I'd like to do is, you know, you kind of like at one level know that you've got a bunch of like zeros and ones, you sort of know that, and then you sort of know that you turn your computer on and you get a silly picture of a cat. But there are layers upon layers upon layers upon layers upon layers of hierarchy between those two, and everyone just sort of waves their hands, and not many people at all understand what's going on between the transistor. You know, they don't understand what's going on between, you know, an individual transistor and the silly picture of the cat. Okay, and I'd like to really do a series at one point explaining how integrated circuits are made and how they work and what are those different hierarchical levels that you work with. Okay, good question, Sunil, on zeros and ones. I said later, I wish I knew. Okay, I'm not sure sometimes what you guys are talking about. If you have a Logitech, you can use Logitech webcam software to unselect autofocus and set it to certain focus. You're right, Charles. And then, then I moved my camera and wished that it was autofocus. So, Charles, I think maybe you're right. Maybe I should do that. Chemistry is indeed a pain. And I don't like chemistry because it doesn't make sense. Physics is good because math makes sense, right? Math makes perfect sense. Physics makes perfect sense. But chemistry, it's like, well, it's sort of like this, but, it's kind of like electrons orbiting, but not really. And then, well, it's really a wave function. And if you think about it, we're really not even sure if the electrons are there or whether the universe really exists. It's just like chemistry. Man. It's messed up. Okay. Never did that. Hi, Paul. Who was that? Hi, Paul. Who was that? Just checking in. Drunk engine. Yeah, very good. Okay. I heard sound only. Mini AC motor. That makes sense finally. Good show. Okay, good. Very smart. I'm really enjoying this live. I am too. I enjoy these live chats because I'm in there with our kind of core group of people. How do you make the springs? Okay, the springs are out of polycrystalline silicon. Okay. Polycrystalline silicon, like a paper clip, if you bend it like 20 times, it breaks. You get like metal fatigue and it breaks. Polycrystalline, you can bend it infinitely many times and it never fatigues. So just like the wafer itself is silicon. Okay, the wafer itself is silicon. Well, the silicon in the wafer is single crystal. And what does that mean? That means that every atom is in its perfect spot. Okay, every atom is in its perfect spot. You have this crystal lattice that is formed. I am doing an amazingly good job at drawing this crystal lattice. Okay, and then there's like one in the center, and then there's a couple more in there, but you have this tightly placed perfect crystal. That is what the silicon wafer is. But you can't just lay down a perfect crystal. When you put the silicon layers on top of the glass layers, they go down not in a crystalline form. They sort of have little chunks of crystal around, but it's polycrystalline silicon. It's a little more organized than amorphous. But that polycrystalline silicon, I am telling you guys, you can flex that forever and it doesn't you can flex it forever and it doesn't fatigue. And so let's make a spring. Okay, here's the silicon wafer. I expose it to oxygen at high temperature, and what do I get? Somebody tell me, what do I get? What happens? I'm going to see if anybody actually paid attention last week. What happens if I take a silicon wafer and I expose it to high temperature and oxygen? What do I get? Class? Class? Okay. Is anybody out there? Is anybody going to answer me? What happens when you expose a wafer to oxygen and high temperature? Okay. I'll answer a question while I'm waiting for you guys. Can you show us how to use the microcontroller of the Arduino on a PC board? I'd love to do that. I'd like to kind of build up an Arduino from scratch, just starting with a chip. I would love to do that. CPUs or some ICs often come with a mirror-like surface. What's the purpose of the mirror surface? Okay, the reason it looks like a mirror, Bob, is because that in order to build things like on the atomic scale, you've got to start with a surface that is atomically flat. And if you start with something that's atomically flat, it's going to look like a mirror. Okay, a really good mirror. Common, bingo, silicon dioxide, also known as glass. Okay, so what we're going to get is we're going to get a glass layer because we put oxygen and again kind of atomically flat, which is hard for me to draw, but kind of an atomically flat layer of glass. And then what am I going to do? I'm going to photo pattern and etch this little thing. And then I'm going to deposit polycrystalline silicon. I'll make that a different color. I'm going to deposit polycrystalline silicon. Okay, and then I'm going to photo pattern that polycrystalline silicon. Okay, and it's going to come down into this hole. So right here, that polycrystalline silicon is going to be anchored to the substrate. Now I'm going to dip this in hydrofluoric acid, and that is going to eat away the glass, and I'm going to be left with this tiny suspended piece. And again, this is cross-section, right? This is cross-section. Well, how would you make this a spring? You would want to then photo pattern it as you were doing this, where it's very, very long and very, very thin and very, very narrow. So you see, if I have something very long and very thin and very narrow, it is a spring. Sort of like, imagine this ruler, right? You can think of this ruler as a spring, but because it's thin, well, imagine if I made it thin in this direction as well, then I have a spring. That's how we make the spring. Okay, so that answers the question of how we make a spring. All right, you guys, let's take a second and ask more questions, and then I'll jump in and I'll talk to you a little bit more maybe about how we make the, how we would make a 9-axis from this kind of. The 9-axis is really very, very similar to a motor. It's very, very similar to a motor. Okay, am I going to get any questions? Am I going to get any questions out there? What have we got going here? You guys don't have any questions? Or am I just dealing with the 30-second lag time here? Man. Is anybody out there? Okay. Says that we're live. Nobody is asking questions. Okay. Got some guys. Francis. Silicon dioxide. Yes, sir. Bob. Yes. Just do it. Okay. What is my favorite Arduino? I like the Arduino Nano is my favorite Arduino. Okay. I don't know if you guys just are not asking questions today. Nano motor, nano generator. Well, didn't I show a nano motor? Didn't I show a nano motor? And, kind of like you could make a nano generator, which would mean that, if you were shaking something and that thing was moving back and forth, you could kind of try to harvest that motion. It's a change in capacitance and try to kind of make a charge pump off of that. It's a little bit hard to do. Okay, you guys are not asking questions, so maybe I'll show you some of the things of what might be going on with this accelerometer. So we need an X accelerometer, or an X accelerometer, a Y accelerometer, and a Z accelerometer. All right, so let's look at how we would do that. So from a cross section, here's the silicon wafer, and I'm not going to put in the details because at this point you know that I can deposit, I can photo pattern, and I can etch. How do you make a nano power supply? Really, it's very hard to make a nano power supply because the power that you can generate in a battery scales as like the cube of the volume. So when you get to microscopic dimensions, you would have very little. Energy. All right. So remember how we could make that diving board? Okay. So this is our diving board. As we move up and down with an acceleration, remember what happens with acceleration? Force is equal to mass times acceleration. Force is equal to mass times acceleration. So when I accelerate this whole thing up or down, what is this diving board going to experience? It is going to experience an acceleration, and that acceleration is going to generate a what? A force. Well, if I move this up, it's going to experience a force down. And then what's that going to do? It's going to kind of bend it over. And now I'm going to have a different D. And so what I'm doing is I'm measuring the capacitance between this and the substrate. C is equal to epsilon, a constant, A, a constant, over the gap, D. So any change in capacitance, I can calculate D. Okay, and then from D, you have kind of like Hooke's law, right? That I can, it's like force is equal to K times x, where x is the displacement. And so by measuring capacitance, I can calculate D. From D, I put that in as x, and I can calculate F. And then from F, I can calculate A. So by measuring capacitance, I can directly then calculate accelerometer. And so that is measuring acceleration in the z direction. Now, initially, what you can imagine is they made 3 of them, and then they mounted one like this, and that z-axis acceleration. They mounted one like this, and that was x-axis acceleration. They mounted one like this, and that was y-axis acceleration. So that was kind of like back in the old days. But then what they did is they said, okay, well, let's just build them, because we don't want to assemble these things. Let's just build all 3 at once. And so here is our chip, okay. And then here was that diving board. Okay, so now we're looking down on it. And so it's anchored to the substrate here. This is the diving board, and this is that z-axis accelerometer. Well, here what I'm going to do is I'm going to build these fingers again, like this. Okay. I'm building these fingers, and then remember this movable part that went in here like this. I got to draw better than that. I didn't leave myself enough room. So let's say that I'm going to build. These were the fixed fingers. Okay. Remember those E's that we had. These are the fixed fingers. Remember those E's that we had. And then this was the movable floating center part. Do you guys remember the movable floating center part? Okay. So now, remember this center movable part is suspended by springs. So if I move it like this, what's going to happen? This thing is going to experience a force this way or this way. Now, the gap doesn't change, but the capacitance between here and here, right, the capacitance is equal to epsilon A over D. Well, now D is the gap between here and here. That's not going to change. But if this shuttle moves, what is going to change? The area is going to change, because if this shuttle comes in further, the area of overlap between these fingers grows. Or if it comes this way, the area here gets smaller and the area here gets larger. So you can measure those capacitances. Now I've got a z-axis accelerometer, and this one then is an x-axis accelerometer. Well, what about y? Well, I just build another one of these, only I build it this way. Okay, this is the movable part. Now this one is going to respond in the y direction. So do you see with these 3 structures, I can batch fabricate in flatland with no assembly required a 3-axis accelerometer. And a lot of these first nanotechnology chips were, the first ones were a 1-axis accelerometer. Then they did the 2-axis accelerometer, and then all on one chip they were able to build 3-axis accelerometers. Now, actually in the early days they kind of did it this way, but then they got like really smart and they started getting very sophisticated, and they sort of started making something where they were making one device like this. Okay, with the fingers. You know what I mean, these comb fingers, these interdigitated fingers. Okay. I wish I could draw better. And then they would check the capacitance between here and the substrate. So if it was going like this, that capacitance would change. And then if it was going like this capacitance would change. But then it could also go like this, and then that capacitance would change. So they got really smart where they could build one structure that could measure acceleration in X, Y, and Z. And why would you want to do that? Because you could pack more of them on the wafer, so that this would be like 10 times cheaper, because, you know, you think of the cube, right? It would be sort of like, you know, it would be 10 times smaller than building 3 of them separately. So Smaller you make them, the more you fit on a wafer. You batch fabricate the wafer, so the cost for fabrication is the same whether you build one or a bazillion. So by building these one structures that could do X, Y, and Z acceleration, they saved a lot of, they got the cost way down. Okay, nanomotor, nanogenerator, looks like no questions. Yeah, what I thought, man, you guys, I thought you would be interested in this. I thought you would ask me questions. Will the diving board generate heat? No, the diving board will not generate heat because there's no current flow. If I put a voltage on a resistor, current flows, heat is generated. But when you have capacitance, there's no steady state current, so there's no current being drawn. And because there's no current being drawn, there's no power dissipated. So they're very low power. There's no current, and there's no heat generated. Okay, what's the accuracy of this, guys? Guys, you can measure like atomic displacements on these things. You can measure like atomic displacements. So you can measure extremely precisely acceleration. Now, you design these things for different applications that if you want to detect a car crash, you don't want it to be sensitive. You want it to not break or shatter when there's an event like a car crash. So what you would design for a car crash would be very different than what you would design as a seismometer, where you're trying to look at small changes or, small motion of the earth. Okay. Why do you not your engineering notebook? Why whiteboards? Okay. Yeah, the problem is when I use my engineering notebook, my hand is like this, and you can't see what I'm writing because my hand is in the way, and then the ink doesn't show up very good. And so I wish I had a better system where I could write with a pen on an engineering pad and you could see it, but let's work on that. Let's see if we can come up with something good. Has Moore's Law stopped working? I really think it has. Some people might argue with me, but I wrote Moore's Law, like I started working on this stuff in the early 80s, and I wrote Moore's Law where it basically says you double the number of transistors that you can build on an integrated circuit every 18 months. And I wrote that for many, 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 many generations till I kind of got out of the integrated circuit. Like I was responsible for an integrated, I managed a $1 billion integrated circuit manufacturing facility, and I was there from the early 80s to about 2000. And about 2000, it was like you were running out of steam on Moore's Law. You were really starting to hit some fundamental roadblocks. And so I think that you're going to have to do something drastically different. I think that you're not going to continue to pack more transistors. Now, you'll get more computing power, and there's always another trick they can pull. But it's not like just for those, for those 30 years or whatever where they kept doubling. I don't think they can continue to do that or are continuing to do that. Okay, interested in listening to something new? No questions. Okay, are there mechanical wear and tear issues on these kind of machines? Okay, excellent question, Cap. This is the thing. You think mechanical elements wear out. Why do mechanical elements wear out? Because they have rubbing surfaces. Your engine wears out because you have rubbing surfaces, and you put oil on it to try to limit that. Everything that we did in the micro world, we never had rubbing surfaces. We only had bending and flexing. Okay, we would bend, we would flex, but we would never have a rubbing surface. Let's see if I can kind of show you that. We're barely hanging on here as far as this thing, as far as not crashing. We somehow got corrupted on that. We somehow got corrupted, and I couldn't show you those pictures. Let's see. So I'm looking for a good video here. That's not it. I know you're not seeing it. I'm just going to find it before I throw it up here. Man, I'm having trouble finding my... Oh, this is it. Okay. Okay. I think I can show you this. Okay. So this is one of these microscopic machines. It's a mirror. And what you can see is you can see the big mirror here that we're using to steer optical signals, like for a cross connect switch. Oh my goodness, no, no. Let's see, how do I get back over here? That was, man, this really, really, really annoys me. Okay, I need to hit, I think if I hit this, it'll, okay. So you see, you can see that mirror. The mirror is microscopic, like you wouldn't be able to see it with your naked eye. But you can see it's huge. These are the motors. So you can see I've got a huge motor here, a huge motor here, a huge motor here. And we were generating so much force, we could have just ripped that mirror apart. We were generating so much force, okay? But what you can't see is this motor. Remember how I showed you the picture of the motor and I drew like 3 fingers? Imagine that it wasn't 3 fingers, it was 3 million fingers, okay? Like 3 million fingers, like 1 million fingers on this motor, 1 million fingers on this motor, 1 million fingers on this motor. And then when you apply that voltage, you pull, and when you pull, then you have this extremely sophisticated design. And then you see I can make it go straight up and straight down by having all 3 motors work together. But if I have these 2 motors working against that motor, it's going to tilt like this. Or if I have these 2 motors working against this motor, it's going to tilt like that. So you coordinate the electronic signals that you're sending to the motors, and you can make the mirror do anything. But on this, you don't have anything that rubs. It's all done with springs bending. There are no surfaces that are rubbing. And because of that, these things will last forever. Like we took many thousands of them out to many, many billions of operations and could detect no changes whatsoever in the spring constants. Okay, so let's come back over here. Let me see if I can get back to your questions. Now, that was a good question. Okay. All right. I like it when you guys ask questions. Okay. Can this be used? Okay, let me see. Let me get back. I got some good questions coming in. Mechanical wear and tear. It does not wear out if it's made of polycrystalline silicon and if you don't have rubbing surfaces. The accelerometer makes sense. What about the what's reading the value of the capacitance? An integrated circuit. I showed you the part where we were building the machine, but then we're building integrated circuits right beside the motors. And measuring capacitance is a circuit. So you just build a capacitance meter right there beside your device. That was a great question. Okay, can this be used as a nanoscopic weight scale? Yeah, you could, because if I had that thing suspended and I dropped some little something on it, what's that going to do? That's going to pull it down a little bit. What that's going to do? Change the capacitance. What's that going to do? Yeah, you could make a little tiny scale out of that. A magnetometer, how would that work? Well, imagine that we had that diving board and I put a magnetic material on top of it. If I lined up with the magnetic field, it's going to pull it this way. Against it's going to push it. So if I put a little magnetic material, and to do a magnetometer, you have to violate my rule of no new materials. You would have to put a magnetic material, and then that magnetic material that's on a diving board, it would generate motion as it experienced the force of the Earth's magnetic field. How about that? I don't know what Max Tegmark says regarding artificial intelligence. First of all, I think artificial intelligence is a little bit of a misnomer, because it was kind of like when I showed you the Jetson Nano and I showed it a picture of itself and it thought it was a lawnmower. You know, it's not thinking. All it is doing what you programmed it to do. And then as we get more and more computation power, we're teaching it more and more and more special cases, okay? But it never goes beyond what we taught it. So, you know, like it can't infer things. Really, I don't think artificial intelligence can infer things, but as computation power increases, what happens is we can train it for more and more and more things. So imagine that you went to Google and you downloaded a bazillion images, and then you looked at the file name, and you think that file name probably has something to do with what the picture is, and then you just turn your image recognition loose on a gobbledygook bazillion Google-licious number of images, and then it starts recognizing things. But it can never infer anything. It can never infer a relationship, I don't think, that it hasn't been taught. So I think that it's just more power lets us train a computer to do more things, but it just isn't getting to that spark of like intuition or inference, and therefore it is not intelligent. Therefore it is a highly, highly, highly trained and programmed device that can recognize things that it has been taught. Okay. So the future of AI, things that I'm concerned about with AI is just the ability to collect data and then what they're going to do with the data. Okay. And so it would be things like, okay, let's make things safer by collecting a whole lot of data on everybody. Like, let's create profiles on people, and that way we can figure out who the bad guys are. Okay. Oh, wow, that's great. Who wouldn't want to know who the bad guys are? Like all these mass shootings and stuff. Yeah, let's go out and figure out who the bad guys are. But you know what? Then one day you turn around and guess what? You're the bad guy. So who is it that defines who the bad guy is? And so their ability to just monitor every single thing that you say, everything that you're thinking about. And so even I think you see this on things like the ads that are being fed to you on the internet and social media and the websites that you visit and so forth. It's like it just finally gets creepy. Where are they getting that information? Now, in the old days, it would be like, okay, I visit a website on digital watches, and then all of a sudden it's showing me digital watch ads. That sort of makes sense. But it's getting creepier and creepier, the ads that it shows, and it says, like, how did it know that? And then it's so like, my daughter calls me on the phone, one day, and, she's married, and she was very excited, and she called me on the phone and said that they were expecting a baby. Okay, and so we sat and talked about it. And then I got on the computer and I just called up some random website on Arduino or whatever, and it started showing me baby diaper ads. Okay, how did it know that? I didn't go anywhere, right? How did it know that? And so it could just be random, but you do almost start getting paranoid about, is it listening? Like, is it listening to messenger chats, and is it, audio to text what you're talking about and then feeding you ads based on what it's hearing? I don't know. You guys give me your feeling. Are you seeing anything that could be considered creepy as far as ads that you're being fed? So anyway, I think the danger of artificial intelligence is creating profiles on people. And if you think in China, like, they create social profiles, and if you're not supporting the government, your social score goes down. And then it's harder to get a seat on an airplane, or you have higher interest rates at the bank. And then, like, if I socially interact with you and you have a low social score, then my score goes down. So all of a sudden you can just create these outcasts in society that no one wants to even it knows where your phone is, and it knows where my phone is. And if my phone gets near your phone, then my social score goes down, and then I'm paying more interest rates at the bank. So I think all this computation is going in a little bit of a creepy direction. But you guys tell me, am I just paranoid, or does any of this bother any of you? Approximate life I see last a long, long, long time. I mean, you never have an integrated circuit fail, hardly ever. It's always the interconnects. It's the connections between the integrated circuits. The integrated circuits themselves just virtually never die. Now, you can have hard drive failures. Integrated circuits can die because of, like, electrostatic discharge, but kind of like the integrated circuits are going to be the last thing to be to die. Okay, let's see. You say bending or flexing, but what about the gears rotating? Okay, those gears, yeah, where they were rotating, that's going to rub. But the thing is, I showed you those because they're things you would understand. You understand motors and gears and transmissions and things like that, rack and pinions. The real things that we did in real applications, we never use gears. We would use mechanical amplification, but we would never use gears. We would never use anything that rubbed. Okay, the 9-axis series, Randy, I think is going to be about 20 lessons long because I want you to learn it. I don't want you to just go download some code and make things. I want you to learn, right? You're going to learn some math. You're going to learn some programming. You're going to learn some good stuff, okay? How long will any version of MEMS that reads rotation? Yes, like that's how the gyro works, right? So this is 9-axis. I told you about Z-axis acceleration, Y-axis acceleration, and X-axis acceleration. You understand that. So how does the gyro work? All right, good question, man. We've talked about magnetometer. Okay, so I've got to kind of step you through it in baby steps. Okay, but let's say that just magically, okay, I create this floating disc. Okay, this is a floating round disc, and you're looking at it from the side, floating above the surface of the wafer. And imagine that it is rotating, right? It is rotating. So this is looking from the side. Here we're going to look down on it. So this is the cross-sectional view. This is looking down at the wafer. So this thing is rotating. Okay, so let's say the rotation is down here and coming up here. All right, so if this thing is really rotating and spinning very, very quickly, what is it about inertia? With inertia, you don't want to change the axis of rotation. So this is the axis of rotation, and it does not, you have momentum, so you do not change the axis of rotation. So if I rotated this, what is going to happen? This thing is not going to rotate. It's going to want to stay where it was. So it's going to want to be like this. You know, that's how a top spins, or that's how you don't fall off a bicycle, right? When you're riding a bicycle, it's not that you're balanced. It's just that that tire has angular momentum, and its axis of rotation, which is the axle of the bicycle, doesn't want to change. And it is that vector on that rotating wheel that is keeping you from falling over. So same thing, if this is rotating like a bicycle wheel, if this wheel is rotating about this axis, then no matter what you do with this substrate, this in the universe wants to stay where it is. So if I rotated the substrate, okay, like this, what is going to happen? This gap, I'm rotating it this way, this gap is going to get smaller and this gap is going to get bigger. So if I measure capacitance between here and here and between here and here, I'm going to see this one getting bigger and I'm going to see this one getting smaller, and I can detect that change in capacitance, and then I know that I have been rotated. Okay, so acceleration is just looking at linear motion, but the gyro is looking at rotational velocity, and it's looking at this spinning element who wants to stay aligned with its axis of rotation. Okay, that, what I've told you, is almost true. All right, what the problem is that you cannot magically create a floating disk that rotates, right? So what do? You put springs on it, and what you do is, rather than spinning all the way around, you vibrate back and forth. And so the vibration of that floating member, it's not going all the way around to create inertia. It's going like this. This has inertia. This has inertia around the rotational axis, And then it is that inertia that makes it want to not spin. And that is how you do the X gyro, the Y gyro, and the Z gyro. You vibrate an element, you create inertia around an axis, and then you can measure rotational velocity. And that, my friend, is how the gyro works. So you got 3 of those, you got 3 magnetometers, and you got 3 accelerometers. Okay, so we've got a biggest fan. Okay, Hamza Ali, thank you for being a fan. I really appreciate that. Okay. Let's see. How long? Okay. Any version of MEMS that reads rotation? Yes, we talked about that. Would nanotechnology things be used inside human bodies in the circulatory system? Yeah, you're kind of going there, but it's a long, hard path to get there because the body is kind of like really dirty. And when you have things that are really small, they're very easy to clog or contaminate. So it's going to be, there's going to be limitations of what you can do in the body because of just the gunkiness of the body is not easy on machines. Okay, it's Ray, that's the thing. It's not self-aware. There's a spark in a person. Like I can tell a person A and I can tell a person B, and the person can go out and take what they know about A and take what they know about B and apply it to C. And my granddaughter's 2 years old, and so I'm very interested because I'm interested in artificial intelligence. It's just amazing to me to see a little brain start getting wired up and how they take what they know about one area and they apply it to a new area. And it's just amazing how that brain starts sort of self-learning, self-aware, making inference. And nowhere in artificial intelligence do I see anything that is anywhere like that. Can't we teach it or something like that? Just thinking. Well, there's a difference between monkey see, monkey do, and that's kind of what artificial intelligence is. It's kind of monkey see, monkey do, but it's not like, if I got that rock over there, and if I threw the rock at, this coconut up there, I could knock the coconut down without having to climb the tree. Okay, you see, the computer can't think that way. What it thinks is rock. It's this big, it's this color. You teach it to measure the weight of the rock. You teach it to measure the color of the rock. You teach it to measure the composition of the rock. But the computer's never going to think, hey, somebody should pick that. And even though a computer doesn't have arms and legs, it's never going to think, hey, buddy, if you went and picked that rock up and threw it, you wouldn't have to crawl up the coconut tree. You see, the computer is not there, and that's what intelligence really is. Okay, can the gears rattle out of place due to high vibration? No, they're constrained really good. They got a hub on top. Robocalls are creepy ads that pop ups with things that you have researched online. Power of AI is invasion of privacy. Yes, that's the thing with what we call artificial intelligence. It's really data gathering and analyzing data sets. It's analyzing data set, and that can be good or that can be bad. Film Factory believes that it's listening to our phone calls. I spoke to a friend on the cell phone, mentioned a magazine I liked as a child, never Googled it. All right, Film Factory, boom, that's what I'm talking about. And I'm seeing that happen more and more. And I think some of these smart devices, certainly, oh my goodness, the Nest and this Echo stuff and this Alexa stuff and even the Siri stuff, man, that stuff is just not, I don't like that. I think that stuff is an invasion of privacy. And I am seeing other people in your comments saying they believe that they are gathering data in ways that would be surprising. Like maybe your family is sitting watching TV and maybe the TV is thinking, maybe the TV is listening to what your family is talking about and reporting back to the mothership. Okay, there's a Black Mirror episode about Social Score on Netflix. Okay, I don't get Netflix either. And guys, the thing is, it's just like I've said it before, I am a doer. Okay, I am not a watcher. If you happen upon me one day, I'm going to be doing something. I'm going to be programming something, building something, growing something, cooking something, making something, designing something, inventing something, fixing something. I'm not going to be watching something. Now, YouTube is good because I learn on YouTube, but I don't consider that watching. I consider that learning. Like, hey, I need to know how to load this library. I'm going to go to YouTube to learn, so I will learn. Learning is doing, but I just don't do things for entertainment. To me, entertaining is creating. Okay. So let's see what we've got here. Oh, I've experienced that too. I had an argument with my friend and we decided to Google the right answer and I just typed the first letter. Yep. It's creepy how Google autofills as you start putting in a search term. And it is my perception that a different person on a different computer could start the same sentence and it would figure it differently, that it's almost got you nailed personally in how it answers the question. Okay. Is it too late for a 21-year-old to start learning electronics? Andy, of course not. Start learning it, man. Start with the first my Arduino tutorial series, then go in, learn the Raspberry Pi, then go in and learn Fusion 360, and then start doing some circuit stuff. Oh man, 21, you're a young whippersnapper. Ready and willing to learn. How do MEMS or our phones know true north? Because there is a magnetic vector and it is detecting the Earth's magnetic vector. That is how it works. Okay. Andy, learning stops so no, it's never too late to start learning. Some guys are like 80 years old and they're taking my Arduino classes. Vibration on a MEMS gyro part's wings are flying dragonfly. Piezoelectric effect can be calculated using proportional relationship. Yep. Abstract learning. Alexa is always listening. Yes, it is. And that's why I don't have Alexa. I do my best to turn Siri off. Yeah, back in the day before I threw out my TVs, I actually went in and I threw all my TVs away one day, but I was like getting on my router for some reason, and I was trying to like get the router where it would get a fixed IP address for the Raspberry Pi, and I was looking on the router, and you know what? My TV had connected to the router without my permission, and so it was like the TV was sitting there phoning home to the mothership without even asking me. That was kind of creepy. Okay. Why watch something, do something when instead we can, what? Okay, yeah. Yeah, do it ourselves, right? Yeah. That's why I don't watch golf or I don't play golf. I don't waste time with things. My time is valuable. I'm going to use it for something good. Okay, no, there's a lot of good stuff on YouTube. Is it streaming? Is what streaming? I'm not sure. What is vector stuff? Is that determiner matrix? No, we don't really have to do determinant or matrix stuff for the non-axis stuff. It's really cross product, okay? Because like if you look at my little, oh man, I lost my little arrow. Okay. But like imagine with this, let me come back to a cooler view here. Okay. So imagine I have a vector coming out this way and I have a vector pointing out. Well, I need that orthogonal vector coming this way. So I take this vector and cross product, and I get the vector out that way. So most of what we're doing is trigonometry, and then we're going to be doing dot products and cross products, if you're asking as far as the non-axis stuff goes. I started with Fusion 360. All right, yeah. I don't know much about Fusion 360. I'm not very good at it. But I got you started. I'd like to go back and learn more on Fusion 360 and get back to that someday. Make more videos on interfacing Arduino with other languages like you've done in the Python. Okay, yeah, that's a good suggestion. I'll be surprised how many guys are talking about privacy here while they are putting themselves every day for sale on social media. Yeah, you're right. But kind of like when I'm on social media, it's like, I'm putting it out there for everybody. You guys can follow me on YouTube, look up Paul McWhorter, send me a friend request, right, if you want to follow me on social media. But that's my kind of public persona. But, there's a more private side, like, when I'm sitting around talking to my family in the house, I don't want people listening to that, okay? And so you're right, social media really is it's like you're handing them all your stuff. Okay, I'd be surprised how many, okay. Apple pretended it was just a bug, and yeah, just a bug, right. Oh, what? Did I steal all your data? Oh my, I'm sorry. How did you know older guys are learning the Arduino programming? Oh man, they are writing me every day, and I would say, man, there are hundreds and hundreds of people in their 60s through 80s that are going in and learning this stuff. Like maybe a guy that was an old CAD guy back in the day, a draftsman, or a guy into ham radio, technicians. These guys are coming back and they're going strong. I don't know if I would use a Raspberry Pi for industrial purposes. I mean, vector stuff in mathematics and programming. Okay, I use a lot of vectors in math and programming. What time do you usually go to bed and get up? Curious. Okay, I don't have an alarm clock. Man, 5 o'clock, I'm out of bed. Some days I wake up at 4, so I am up and out early. It's just like, man, I get up and I jump out of bed. I'm not tired in the morning. I wake up fully awake and ready for action. And then I'm in bed by 10 o'clock, and sometimes maybe sometimes maybe I'm tired. Maybe I'll go to bed at 9 o'clock because I get an early start. What are your ideas for Design Spark PCB, sir? Would you recommend it for PC design? I'd like to learn PCB design, but I really haven't. I think it's the way to take our projects to the next level. Like if we could do 3D printing in Fusion 360, and if we could design PCBs, we could take our projects to the next level. Okay. Can you explain how color sensor in the camera works? Beyond the scope of this conversation, I really can't give you a simple answer for that. Okay, very nice. Okay. Any tutorial on I2C, serial, or SPI? That's probably something that's needed because I don't think most people understand it. I think it's just something you just kind of use the library, and we should probably learn that better. Who has coffee? I was waiting for lesson 24 of the new Arduino yesterday. Oh, okay, yeah. All right, everybody was complaining because they wanted me to release the new 9-axis, and then when I did, then people got upset when on Thursday they didn't get their second Arduino lesson. But guys, you see, the thing is, if I just do the beginner stuff, then the more experienced guys get bored and they leave. And then if I do the advanced stuff, the beginner, so on Tuesday, I release the beginner series tutorial on Arduino. On Thursday, I release the advanced project, the 9-axis. And maybe when the 9-axis one is done, maybe then we could get together and figure out whether we wanted to do the Jetson Nano. I am so excited about it, but I am not going to do it if you guys are not going to follow along. And what I can see is nobody's ordering, at least from my links, no one's ordering the Jetson Nano. Now, bukus of people ordered the 9-axis, so that says a lot of people interested. I make a video series, lots of people are going to watch it. But I'm not seeing that same interest in the Jetson Nano. Maybe I should do another video that shows you guys what it is. But also, maybe that's not something you're interested in. So it makes sense for me to work on areas where people are interested. Okay. James, 73 and still learning. There you go. You see, you're one of the more mature among us, so that's good. What are your comments on, is Arduino a skill that you can write in your resume for a company? Because my teacher says that it is making us away from core electronics. Well, I'll tell you what you do, Anurdua. I'm sorry, I can't pronounce your name. You make a cool little project with Arduino working with a circuit, and you put it in your pocket. And when you go for a job interview, you whip that baby out and you show that guy that you're interviewing that you've done something that is programming and microcontrollers and circuits and innovation and PC design and 3D printing. You'll be in. You'll be in. Next live video should be on Arduino technology architecture. Man, I don't know where the Arduino is going. it's like the whole thing is you had the Arduino Uno, and then if you wanted something small, you had the Nano, and if you wanted something big, you had the Mega. But now I go to the Arduino website, and I can't even figure out what they're doing. It's like there's 100 different boards, and it's just a bunch of chatter, a bunch of techno battle, like, oh, we've got the ARM 364 reverse gig 356 blah blah blah. It's a bunch of techno jargon, and I have no idea what is it, why would I want it, what does it do that I can't do now. And so I have no idea what the future direction of Arduino is. If I want some, Arduino is very simple to interact with the outside world. And then if I want to do something more sophisticated, I can send it to Python on the PC, or I can use something like a Jetson Nano, which has the GPIO pin. So you see, I see things in these little clear templates, and I have no idea what they're doing over at Arduino. I have no idea where they're going with that. I don't know how to explain how a color sensor in a camera works. I don't know how to explain that. Here it is 11:30. Man, I've been going for an hour and a half here. Maybe release the videos on faster on Patreon. You know what, guys? I really appreciate you guys that are supporting me on Patreon. But man, the one thing I am committed to, this is a labor of love, and everybody is going to get everything for free. Okay. And you guys that are helping me, thank you. And you're really, really encouraging me. And what you do is when you help me, it's like, yeah, go make more videos. Not because I'm getting money, but because I know that it's useful to people, because they're tangibly showing me that it's useful. Okay. But what I don't want to do is, there are people in the third world that are watching these videos to try to make their lives better and to try to work their way out of the situation they're in. And I'm not going to cut them off or give them second-rate content because because they're not paying on Patreon. And so the reason I don't release things faster is because, like, if I start getting too many videos on things I'm subscribed to, I unsubscribe just because I get tired of it. So I think that I could do 2 videos a week, an introductory video, a more advanced video, and then maybe try to do 1 live stream a week. And that keeps us all kind of friends, and takes care of the people who are new, takes care of the people that are looking for something more complicated. But one of the things is like, I won't use the name, but these online educational things that start like with a U. Okay, yeah, there's really 3 or 4 of them, like the Master Series and this. When those things came out, they all were all over me, wanting me to put my stuff behind a paywall and promising me some pretty big bucks to take my stuff all off YouTube and put it behind their paywall. I'm not going to do it. Okay, why? Because what I love is, I love the technology and I love teaching. And that means I want to impact as many people as I can. And really, the best content on YouTube is the free content. Who goes behind a paywall? The people who love money. Who stays out there free? The people that love the technology and love teaching. And so I'm not like arguing with you, Ron. So I'm not like chastising you. I'm just telling you how I think about Patreon. Sometimes you guys like send me like guys send me coffee pods sometimes in the mail. People sign up for Patreon. People buy that goofy coffee cup with my picture on it. That's a great encouragement, right? But I'm not doing it for that. I'm doing it because I love the subject, and I'm doing it because I love to teach. And then when you guys do that, then that's showing me something tangible. Just like, I spend a lot of time in Africa, and I spend a lot of time working as a missionary. One thing over there is if you give people that doesn't, it's kind of like the same thing. I like to go there. I like to teach. I like to teach wherever I go. But it's always an encouragement when you guys, hook a brother up by using my links, my Amazon links, or ordering a coffee cup or something like that. Okay. I gave you a long answer there. Is designer, okay, we're talking there about PCB designer. That's on the list of things that I need to do. Thanks, I learned the Arduino. Okay, Brian, that's good. If it ain't broke, yep, you can still teach us. I'd like to get into electronics. I'd really like to get into old school circuit design, circuit analysis, operational amplifiers. Man, a 555 timer. You wouldn't believe what you could do with a 555 timer. And the thing people say is, oh, I can do that with an Arduino. Yeah, but if you're going to make something, the world of high tech is about doing for pennies things and not doing them for dollars. So if you're going to make a remote control, you can't afford to put a $9 Arduino in there. You got to do it with components that cost pennies. And so I'd love to go in there and show you guys what you can do with 555 timers, op amps, really get down there and start doing some old school engineering. Also logic design, where you have AND gates, NAND gates, NOR gates. Those are some of those levels between the zeros and the ones and the silly cat pictures. I would really like to start working in there. Okay, Bob, thank you for the kind words. Labor of love indeed. Andy, you're amazing. Well, thank you, Andy. You're wonderful. You're wonderful. Appreciate the kind words. Mr. Dua, because on a resume, every skill counts. Yeah, Mr. Jeff, every skill counts. And man, don't tell them what classes you took. Tell them what skills you have. I don't care how busy you are. I want to know what you accomplish. I want to know what your skills are. That's what I'm saying. Make something and whip it out and show it to them working, okay? I don't know what HMI is. What does hook a brother up mean? No, actually, it's very far from being a Texas term. It's kind of it's more of like a in the hood term, and so I use it facetiously because I would be like the furthest from a cool dude as there would be. So I use that term. It just means help a friend out, help a guy out. Okay. That's a funny question with Raspberry Pi. All right, guys, man, we've been going a long time. How about we try to do this once a week? Okay, so I'm going to kind of shut things off here at 1 hour and 40 minutes. This has been going on a long, long time. Sorry that we couldn't show you all the pictures. A couple of things I would like to do. I would like to have a series where I kind of show you all of those layers between the zeros and the ones and the atoms and the silly cat pictures, kind of learn about how integrated circuits are made and some of that hierarchy that's going on there. Would love to teach you, just a lot of different things. How does a transistor work? How does a transistor work? A lot of cool things I'd like to teach you. So hopefully you guys will stay tuned. You guys think about giving us a thumbs up, subscribe to the channel. Think about hooking a brother up, right? You guys, it's an encouragement to me when you sign up for Patreon. Makes me want to make more videos and keep this thing going. And then, use our links for your Amazon stuff, okay? Talk to you guys later. Paul McWhorter, TopTechBoy.com. Had fun today. We'll talk to you guys later.